Can you see the presentation?
Yes, sir.
Okay, fine. Okay, so just like the previous week, I am starting this week. This is regarding questions of assignment of week 2. And first, I need to introduce myself. I am Moina Ghoshal, and I am a PhD student at ISAR Kolkata, working on with a specialization in physical chemistry, and I have been assigned as the TA for this course, which is application of spectroscopy method in molecular structure determination. In simple words, you will say it is organic spectroscopy. And the last week I have discussed about the spectroscopy, how spectroscopy is developed, what is spectroscopy, and different terminologies I have discussed, like what should be the population reference, or how NMR was discovered. Okay. Now in this week we will and then we have seen that if all protons in a molecule behave similarly, then you are expected to get only one line if all protons are same in a molecule. But that isn't the case. That isn't the case. Okay. So in that case, you see that this frequency that NMR frequency that you often when you do NMR of any compound, that is completely dependent upon the environment of this proton which is residing there. And then we have seen that how which proton gives where peak, and also we have also seen that the deshielded protons, that is where the electron density is less, there means it will shift to the higher field. Okay, it will have high delta value, and that the part which is more shielded, that will give you lower delta value. That much discussion was done in the previous week. So whatever was discussed in the previous week, that is actually called first order spectra. Okay, first order NMR spectra. But you know, life is not so different, not so easy. So what I have mentioned, that life is not so easy. So always only second first order spectra is not observed. Sometimes it happens that second order effects are observed. So every time that the second order effect is observed? No, not always. When second order effect is observed, suppose you have one or two multiplet peak, kind of doublet or kind of triplet peak. So the intensity that you expect according to Pascal's triangle, they doesn't follow. Okay, they will change in the intensity, they will change the relative position, and when this happens, then there are two difference between this delta value of two hydrogens divided by this coupling constant is less than 10. Okay, so when these two are very close, there is a chance that what happened, that second order effect are observed. And what is second order effect? As I have said that that the whatever you are expecting from this first order effect, that is the splitting of the peak, the Pascal's triangle formula, all this, that will not match. They will be completely different. Someone's trying to join. It's already 7:10. Okay. Now there is something which is called AB kind of spin system, which has 4 lines, but the spacing and intensities that depends upon this value, delta nu by j. Okay, so delta of delta divided by j. Okay, so this actually implies that a spin system in which two different protons, Ha, suppose I have two different protons, one is Ha and another is Hb, whose chemical shift are very close to each other. Okay, in that case, what is expected that this Ha and Hb, they are supposed to show doublet for this, and the doublet of 1:1 ratio peak, that is not this present. Okay, so I should write it here. So initially it is expected that suppose there is a doublet, okay, like this, and here is another doublet. Ignore my drawing, just understand the concept. Okay, so this is called second order spectrum. Okay, this difference is J, this is not J, but in your quartet, what do you expect? The ratio is 1:3 is to 3 is to 1. The ratio of 1 is to 3 is to 3 to 1, that you expect. Okay, and the difference between them, any of them will give you J value, that is expected from a first order spectrum. But in here you can see this is a first order quartet. The first order quartet. What is this? This is second order AB quartet. Okay, AB kind of quartet. What is AB? AB are two different kinds of proton that has very close delta value. Okay, so this have 4 lines and the spacing actually depends upon them. Okay, now there should be some difference between this first order quartet and AB quartet. Whatever you are seeing here, whatever you are seeing, that's first difference you can see that the difference between the peaks is not always same. Here it is J, here it is J, here it is not J. Here it is J, here it is J, here it is also J. So in first order quartet, the difference between the positions of the peak is actually equal. But in case of second order AB quartet, it is seen that the difference is different. Okay, and also I have drawn it a bit wrong. Generally, it's supposed to be like this. It is a bit higher in intensity. Similarly, here it will have a bit higher intensity, like this. Yeah, now it's okay. Okay. So also, if you know this position of this delta value, this is in between them. Okay, this is symmetrically stretched. But here you cannot tell where is the delta A and where is the delta B. Okay, this if you think that this is delta A, this is the delta B, the middle point here, it is not delta A or delta B. You see the intensity here is much higher. So delta A must be present somewhere near this. Okay, somewhere near this. Or and it seems also same thing for delta B. So this difference is J, what I was talking about. This difference is J, but this difference, this is not J. What is J? J is the coupling constant. Okay. Now, what I was also telling that what should be the average position of delta A. If you think this is the delta A position, and if you think this is the in between them, it is the delta B position, this is not correct. Okay, this is not correct. It will be correct if your system is AB, not AB quartet, this is the first order quartet. If the system is a first order quartet, then you can say this middle point is delta A and delta. But here this is not the case. So your delta A will be somewhat shifted toward this, and similarly your delta B should be shifted toward this. Okay, because you can see the intensity is highest here and intensity is also highest here. So the peak positions, the average positions, that will be shifted. Now how can we then calculate this average position? Yes, you can calculate. You can calculate this average position delta and also the J value of this AB quartet using this formula. Okay. This is nu 4 minus nu 1 into nu 3 minus nu 2 under root. So if this is nu 1, this is nu 1, this is nu 2, this is nu 3, this is nu 4. You know what I am saying? That difference between this nu 4 and nu 1 into difference between these two under root, this will give you the delta value. Okay. And now delta A will be from the middle position, this half will be delta A equal side shifted. Okay. And how will be J value? J value will be nu 4 minus nu 3, it is this one minus this one, and also is this one minus this one, these are same. Now, different types of systems were analyzed and ABC kind of system, A B prime, B prime kind of system, and A prime X prime kind of system. So, can anyone tell me what is the difference between A prime, B prime, and this A prime and X prime kind of system? What is the difference? Terminology difference I am asking. Can anyone tell me?
Chemical shift.
Chemical shift? Yes, carry on.
Sir, chemically equivalent but magnetically non-equivalent.
Yes. And what is the difference between B and X? That's terminology I am asking.
Sir, B and X are chemically different protons.
How much different? How different you are saying? That is A and B different, B and X also different.
Complex spectra is A, B.
Complex spectra and AX is a you were saying that it's simple, comparatively simple to this, right? What I'm actually asking, what is the difference? Yeah. What I am asking is A, B, and X. Okay. Suppose you are saying that all of them are different protons. Okay. Then why I need two different terminologies? If I need to mention this one is A, another is B, then why I need X? I don't need any X. Or if I made something X, then why I need B?
Sir, X is more deshielded. It has high chemical shift value. That is, A and X has their difference is more.
Yes.
As comparison to difference between A and B.
Exactly. Exactly that I was wanting to hearing. Yes, that is exactly that I want to hear. That A and B, these protons are very close to their value of chemical shift, but A and X that are very much far. Okay. So what will be the example of A prime B prime system? Any para disubstituted compound. Any para disubstituted compound. Again, a poor drawing. Pardon. Yeah. Suppose suppose I am taking some compound. Okay. This compound. Okay. This hydrogen, this hydrogen, this hydrogen, this hydrogen. So this HA suppose, and I am naming it A prime and A prime. Suppose this is HB and this is HB prime. Okay. So this is a para disubstituted compound where these two groups or two positions are occupied by some functional group that is getting these protons HA and HA prime. this exactly HA and HA prime, these two are chemically, you see this chemically equivalent. Okay, you can clearly see, because this H is ortho to this hydrogen, this methyl group, and this is meta to this OH group. Similarly, this hydrogen is ortho to this methyl group and meta to this OH group. So they should be equivalent, but they are not equivalent. Why they are not equivalent? They are chemically equivalent. They are chemically equivalent, but magnetically not equivalent. Why? Because the coupling constant of this A to B and this A to this A prime to this B, this is completely different. If they are same, you can say that they are magnetically equivalent, but they are here not magnetically equivalent. So they are designated using this terminology. This is A prime, B prime system. So what is the advantage that you will get if you know this kind of system, or you will see this kind of spectra? So if you see any kind of spectra like this, where there is a pattern of A prime, B prime kind of system, you can clearly say that this is a para-disubstituted one, right? So in the next part that just okay. So now you have seen how second order effect are generated, okay, in which cases second order effect are generated. But in when you are going to analyze any NMR spectrum, you don't need any complexity, right? You don't need any kind of complex situation that should arise there. So to simplify that second order effect, there are few ways you can do that, okay. The first use is use of high frequency NMR spectrometer. One is that. Another is selective double irradiation, and the third point, which is lanthanide shift reagent. These three things are possible here, okay. By these three ways, one can easily simplify the second order effect. So first, coming to the first point, use of high frequency NMR spectrometer. How does it simplify? So you know that use of high frequency spectrometer, actually the separation between the NMR peaks that actually increases, okay. In a 60 megahertz NMR spectrometer, if you see these two peaks are like this, in a 600 megahertz NMR spectrometer, you will see the peaks difference like this. But what is not changing there? If the positions are also changing, so you seeing the shift are changing, but the J value, the coupling constant, that actually doesn't change. Okay, so what is actually observed? This delta nu by J, right? This was your the terminology upon which based upon which you are telling that this is a second order spectra or it is a first order spectra. If it is less than 10, you can say that there is a second order effect, and if it is greater than 10, then it is a first order effect. So J actually you cannot change. So what is changing? You are changing this delta nu. Okay, the separation between these peaks. Okay, so if you separate it, then you can say that it is a first order. It is becoming a first order spectrum, and you can easily resolve it that who from which it is coming. Another way is the double irradiation. Okay, what is the double irradiation? Irradiation of a spin selectively with a second radio frequency. Okay, so you are saturating one spin. Okay, so what will happen? That spin, since it is saturated already, so what is then by saturation? Saturation means there is no difference in the population of these levels. If you have seen my last week's assignment solving, I have told you that for any spectroscopic transition to happen, you must need to have some population difference. If saturation happens, there will be no population difference. Okay, since there will be no population difference, so it will not contribute to the NMR. In simple language, it is not actually coupling. You are just completely decoupling it. Okay, you are just completely decoupling it. What will happen? One frequency will not disturb the other. Okay, another thing is that if you want to analyze this use is in ABC kind of system where 3 spins are mutually coupled. Okay, 3 spin coupling. There are 3 spins A, B, C. Suppose I do it here. A, B, C kind of thing. Okay. So what is ABC? ABC is in the case where 3 spins that are mutually coupled. Okay. Now you need to make it much more easier. Complex, since it is a complex, so you need to make it much more easier. So what we will do? You irradiate this pin C. What do? You irradiate spin C. Irradiate spin C, and what you will do then? Since you irradiate this, it will get saturated. Okay. So if you irradiate this spin C and saturate it, what will happen? C will not couple either to A or B. So your system will become a AB kind of system. Now AB quartet, you know how AB quartet is resolved, or how you can see this AB quartet kind of thing. Then you can easily the live will be very simple. Then another thing what I have mentioned that using a lanthanide shift reagent. So one thing is that paramagnetic lanthanide complex of beta diketone. Okay, they can act as a shift reagent. Okay, so how shift reagent is working? Since these effects are actually observed through space interaction, so this hydrogen, so what will happen? The beta diketone, this beta diketone thing, okay. So this thing is actually what will happen that it is connected to suppose this europium kind of thing. Okay, europium is a lanthanide, and this yeah. So a beta diketone kind of thing I was talking about. Suppose this is a beta diketone. There is some suppose lanthanide. Okay, europium 2 plus suppose. So this is connected to this is connected to this. And in your sample, there is some electronegative element that is coordinated to this. So in any branch of here, suppose here is another hydrogen, so that will interact with this. So depending upon the position of this hydrogen, the interaction between this hydrogen is different. What I am saying, this hydrogen, they are actually different distance away from this europium 3 plus or europium 3 plus or any lanthanide kind of thing. Okay, so that coupling actually you are just separating them, you are just shifting them with using a diketone derivative. So how can you calculate this shift? You can calculate this shift this using this relation. This is also known as McConnell relation. Okay, McConnell relation. And what is this theta? Theta is nothing but, if you draw a line here, this angle is theta. Okay, if theta is changing for different hydrogens, so this chemical state values will be changing. Okay. Now coming to C13 NMR spectroscopy. So C13 NMR will have I equals to half and also natural abundance of 1.108. So you can see the natural abundance is very low for carbo 13. Now, two types of in two ways you can just control this NMR. One is CW mode, another is the FT mode. Okay. So in CW mode, what is happening that you can sweep either radio frequency or magnetic field. You can sweep any one of these. Okay. So what will happen that you have just you need to measure every nuclei at a time. If you are measuring carbon once, you are measuring hydrogen once. This will be a time consuming process. But in Fourier transform mode, you are giving a short pulse. Okay, you are giving a short pulse. It is very exciting. Okay, and all nuclei are resonate simultaneously. And just you then just Fourier transform it, you will get what you want. Okay, so Fourier transform mode is actually generally very useful nowadays. Now you see the C13 is recorded under the condition of proton decoupling by irradiation saturation. So bringing you a story about this proton, the C13 recording, that if you know the C13 when coupled to a proton, okay, so C13 coupling to a proton, so they will just proton will if proton interacts with this C13, it will thus split it. Okay, just like in proton NMR, you have seen that interaction of one proton to another proton actually show a splitting of the one signal. Okay, but same thing we can observe in carbon 13. Then what will happen? Since all thing in carbon, okay. Okay. So what will happen? What will happen in C13 if you want to record that the decoupling of this carbon signal when it is interacting with proton, it is generally observed. So if two carbon peaks are very close to each other, and if there are several number of protons, then there will be a mishap or that all the peaks are very close to each other and you cannot separate that. Hence, to make this life simple, people have used proton decoupling strategy. What is this proton decoupling strategy? Proton decoupling strategy is just what I have said. This decoupling strategy that you irradiate sample with H frequency, hydrogen frequency. Okay, you need to irradiate your sample with hydrogen frequency. So what will happen? This hydrogen will get saturated, right? If hydrogen gets saturated, what will happen? This will not get coupled to its carbon. If hydrogen is not coupled to a carbon, what will happen? The splitting that you are observing was with for this carbon, this will not be there. So you will see a simple peak. If you have, I don't know if you have recorded any carbon 13 spectra, you will see sharp lines, sharp peaks. Okay, so this is coming because you are irradiating it with another light, which is actually you are just saturating this hydrogen frequency. Okay, so there is a chance that this C13, so actually it was actually coupling with 1H. Okay, now I can turn it off. Okay, you can see here. Okay, I am writing for right. So C13 actually couples with hydrogen and this gives complex peak. I am just disconnected that, okay, using the decoupler. There is a chance that carbon 13 can couple with the carbon 13. So if in that case, if I use some decoupler, all these informations will come because these both are carbon 13. So the complex pattern is expected here for this carbon 13 coupling, but it is not generally observed. Why it is not observed? Who can tell me? The coupling of carbon with carbon, it is not observed in the spectra. Why?
It will saturate.
No, saturation. Suppose it is C13. Okay, I am seeing a coupling of this carbon with hydrogen, one hydrogen. Okay. So what I am doing, I am saturating this. I am saturating this. So what will happen? It will not couple. This coupling is turned on. You can see on this picture for this. Now, my question is, if there is a connection between two carbon 13, okay, if you want to saturate anybody, then you will get no signal. But this doesn't happen. Why?
So natural abundance of carbon is very low, so the
Very
carbon-carbons bond formation was not good.
exactly correct. The main reason is the natural abundance. Carbon has a very low natural abundance. You can see here 1.108%, only 1% of carbon. Okay, so if you see compared to others, that hydrogen or any other thing, carbon's abundance is very low. So if carbon-carbon coupling is happening, if it is happening, you cannot see it. Okay, so that is very, very, very low in intensity. So you can just neglect that. So another thing is that if you decouple completely this proton, the information regarding this proton is lost during this saturation. So you can predict easily that what is the number of signals expected for a compound. Okay. If you do the symmetry analysis, you can see that for the symmetric carbons will give only one peak. All the symmetric carbons will give similar peak positions, and from there if you just get this NMR spectrum for a C13 NMR spectrum of a compound, if you just count the number of carbon atoms, number of carbon lines, you can say that what number of non-equivalent carbons are present in the compound. Okay. Now, then why should we do this carbon 13 NMR? Carbon 13 NMR is important because in proton NMR, if you have an internal acetylene group, you cannot detect. Because why you cannot detect? Because if you have any internal acetylene group, you cannot detect because it will have no hydrogen. Okay. So in proton NMR, it will give no signal. So how do you know that whether there is an internal acetylene or not? But in carbon 13, you can do that. Okay. You will see different position for this carbon 13 spectra of this compound, which contains an internal acetylene group. Or suppose tetrasubstituted olefin. Similar thing, a double bond C, and these four groups, none of them are hydrogen. So how then can you tell that there is a tetrasubstituted olefin is there? You cannot tell it from this proton NMR. So for that you need to do this carbon. Cyanide, CO, quaternary carbon, that all are detected by NMR. Actually, you can see that all the examples that I am talking about here, all of these are devoid of any kind of proton. So whatever things that or whatever groups that are not connected to proton, you can just detect if it contains carbon. If it contains carbon, you can detect it using carbon 13 NMR. Now, whenever a carbon 13 NMR is recorded using a pulse, you give a pulse, okay, then you just acquisition time will be there, and then you gave some delay. Why this delay is there? So this is the pulse, this is the acquisition, and then you are giving some delay. Okay. So decoupler is actually switched on. You are just switched. You have given a pulse. You have acquisition, and data acquisition is done, and then there is some delay. Okay, in that delay time, there is no pulse is coming. In that time, you are turning off this decoupler. Okay, and whenever you are recording this acquisition, you can stop it. This is a one way. Okay, so why this delay is needed? Can anyone tell me? Whenever you measure a carbon 13 NMR, if you are giving a pulse and after that you are just acquiring some data and you need to put some delay. This delay you don't need to put in case of hydrogen. Why?
Realization time in case of carbon is very low.
Sorry.
Relaxation time in case of carbon is very low.
Exactly. So carbon actually took more time to relax back. Okay, so you need to put some delay so that it completely relax back. But this is not case of a hydrogen. Hydrogen needs to actually relax very fast. Okay. Now, unlike 1H, 13C NMR spectrum intensities are not quantitative. What does it mean? From 1H, from the peak intensity, you can know how you have seen that one math I have done, that from that integration I have said that what is the molar ratio of them. Okay, so it gives a quantitative information. But for 13C, you will see this intensity will be there, but it will not give any quantitative information. Okay. So what is the reason? First reason is much longer relaxation time. Okay. And another is very interesting effect which is known as nuclear overhauser effect, NOE, which is known as also NOE. This we'll discuss in the next slide. So the relaxation agent that is actually used, so this is the relaxation agent chromium ACSE3. Okay, this is a paramagnetic relaxing agent. It actually reduces the longitudinal relaxation. So two types of relaxation mechanism could be there. That is, one is the longitudinal. Another is transverse. So it is also named as spin lattice relaxation. So excess spin energy is given to the lattice and then it is relaxing back. Another is entropy energy factor, which is called spin relaxation. This is also discussed in the last class. Okay. Now the thing we're talking is the nuclear overhauser effect. Okay. So what does nuclear overhauser effect tells us? Nuclear overhauser effect actually change in nuclear overhauser effect actually measures the change in intensity of one spin when the spin transition of another nuclei is parted from equilibrium position. Okay. What does it tell? 13, suppose it's one hydrogen. Okay. So I am perturbing this and I am getting facility from this. This is called nuclear overhauser effect. Okay. I am perturbing this spin of this one hydrogen and I am getting facility that what extra information I can get from this now new carbon which is already binded to this hydrogen, which is already coupled to the hydrogen. This is called nuclear overhauser effect. What depends on this depends on the close proximity of nuclear spins and it's inversely proportional to RQ. Okay, so from this NOE effect or nuclear overhauser effect, you can just differentiate which one is methyl, which one is CH2, which one is CH group, and which one is quaternary carbon. Okay, because for different cases the NOE effect will be different. So this is the equation to calculate this NOE. This is I is the intensity or after the NOE is observed, and this is the equilibrium intensity when there is no NOE, when you have not perturbed any system which is coupled to this carbon. Okay. Now NOE just useful to increase the signal intensities at low abundant and low gamma nuclei when they are coupled to high abundant and high gamma nuclei. When that is observed here, if you perturb this hydrogen, if you perturb it, so this will induce this carbon. Okay, and it will increase the intensity of this carbon. So now how can it increase? So external perturbation actually what happens that in reality what happens that it actually gets it saturated. And also what does mean by saturated? Generally Boltzmann distribution says that If N2 is the population of the excited state, that will be much lower than N1, depends upon the energy gap. Okay. So saturation means it becomes the gap is less. Okay. So N2 almost nearly becomes equals to N1. Okay. So the population, since it is increased, suppose if N1 is same, okay, if suppose N1 is same, if you increase N2 so that N1 becomes almost equivalent to N2, what will happen? Your carbon population, the population of this level will increase. Okay, to make the whole system satisfying this Boltzmann condition, what will happen? Your carbon system will have more population. What will be the effect upon this? If you have population more in the ground state, what will happen? It will go transition mode. What will be the consequence of this transition? Your intensity will rise, nothing else. So by making the saturation of this hydrogen, this is almost making this almost equal population of these two states, what you are doing, you are actually creating more population in the carbon, and that actually increases the intensity of the carbon signal, because the intensity depends upon number of molecules that you transition is going on. If number of molecules is higher that is going the transition, intensity is higher. Okay, so high 1H, which is a very abundant and very high gamma nucleus, that is actually very low abundant nuclei, it is actually increasing the signal intensity. So it is actually giving much more information, or this increase will give much more information about the group that is present here. Okay, so it has two advantages, what I have said. Increase in signal intensity is due to removal of multiplets, and each carbon has a single line. That was I have said in the last slide also. And also the NOE increases the signal intensities of those carbon that we are proton. Okay, so what should be the result for this quaternary carbon? You know, for quaternary carbon, which carbon of what is the quaternary carbon? Quaternary carbon means the carbon has no hydrogen attached with it. 4 different groups are there. Quaternary carbon, it has no hydrogen, it has also no NOE. Now, one thing that when certain relaxation operates through dipole-dipole interaction, the enhancement of this intensity will be given by this formula, gamma H by 2 gamma C. Why? What is this H? H is actually, is it the H always? No. This is actually the formula 1/2 of gamma of this part of system, or the system you are perturbing, divided by gamma of the you are measuring. Suppose you are measuring the same system, that one. Okay, you are perturbing the system, you are measuring the system. You can apply this to any other nuclei also, and so it is observed that for 15N29Si kind of system for which you have a negative of gamma, it will result in a negative NOE effect. Okay, you can see here from this ratio, if it is negative, then you will decrease the NOE intensity. So there will be a negative nuclear overall effect, which is decreasing the intensity. So NOE effect will follow this way, that methyl will have higher intensity, the methyl will have higher NOE, then CH2, then CH, and quaternary has no NOE. Okay, so number of carbons is higher, you will have higher NOE effect. So from NOE effect, you can easily tell that which carbon has which is one carbon you have got. So it is a methyl carbon or CH2 carbon or CH carbon. You can easily tell it from the calculation of this NOE effect. So these are the questions. These are the things that Professor Shankararaman has discussed with you in this module. So there is some questions I want to discuss here to solve these problems of NMR spectroscopy, where the proton NMR values are given. You have to actually predict the what kind of structure does the molecule have using the 1 to 10 module, what I have discussed already. So let's go to the questions. Before that, I think someone has some message here. No message. Okay. Now coming to the question. This is the first question, that you have to identify the structure of the organic molecule from the given data. Okay, so you have a molecular formula C5H10O. Okay, from there You just need to calculate, you just need to understand what is the kind of molecular formula here. Okay. So can anybody do that? Okay, I am going one by one, then you will be able to tell me. Then with the help, we will do that. Okay. So
Sorry for interruption.
yeah,
Can you please explain once again how does the perturbation of one proton can increase the intensity of other C13
okay, okay, fine,
by population? I didn't understand that.
okay. Okay, here you see. Here you are saturating this proton intensity. Okay. So what does this mean? There is always some Boltzmann distribution. Okay. Any kind of transition, any kind of transition is happened between suppose N1 state and N2 state. So there will be some difference in the population that the ground state will be maximum, the glacier state will have low, which depends upon the energy gap of the two states. Suppose. Okay, so when you are saturating this, when you are giving some radiation to saturate, what is actually happening? You are making more molecule to the excited state. Okay, so the difference between the population that was initially there, the difference is actually getting decreased. Difference, that is, initially what is there, N2 is much less than N1, but when you are doing some saturation, N1 and N2 is becomes almost equal. Okay, so N1 and N2 almost become equal. What is the consequence? It's consequence that to make the whole system follow Boltzmann distribution, which tells that the ground state population is much higher compared to the excited state. So what will happen? This is already saturated, it cannot take it. So what will happen? All the many number of carbon atoms will be in the ground state. Okay, so it will undergo transition. So if more number of carbon atom goes transition, so what will happen? The intensity will increase. If more number,
Yes, sir. Thank you, sir.
Okay, you
I
understand?
got it. Yes, sir.
Yes. Okay. Now, here, what I was telling that you have to identify the molecule from this molecular formula. So, if you have given such kind of problems, so what you will do? You first try to understand what is the double bond equivalence. What does this indicate? So what does double bond equivalence indicates? Double bond equivalence actually indicates that how many number of double bonds or similar to equivalent to double bond kind of thing is present in the molecule. Okay, listen carefully, that double bond equivalence tells that how many double bonds or equivalent kind of system that is present within a molecule. So how can you calculate that? This is a formula to calculate is C minus H by 2 plus N by 2 plus 1. So this is the formula. What is this C, H, N? What is the stands? C is the number of carbon atom, H is the number of hydrogen atom, N is the number of nitrogen atom, and 1 is. So in this case, you see 5 carbon atoms are there. Okay, minus hydrogen is 10, so 10 by 2 plus nitrogen is there, no. So if you see 5, 5, 5, 0, 1, only 1 will be there. Fine. So you see the double bond equivalence gives that only one double bond is present in the system. Okay. Okay, you understand that one double bond is present in the system. Now you see one by one data. Before that, if I recommend you to solve any kind of problems, if such data is given, you first see this one, D2O exchangeable. Okay, so there is a one hydrogen singlet, and also this is D2O exchangeable. One hydrogen is there, this is singlet and doing frequency 1.9. What kind of group will be present here? Ring can also be possible, right? Which ring you are talking about? Cycloalkane, if you are talking about this double bond equivalent kind of thing. Okay, so double bond equivalence means that system that is either a double bond will be there, or it could be equivalent to system equivalent to that double bond. It may be ring, it may not be ring. Okay. Doublet or triplet cyclic ring. Doublet ring means what? Doublet ring doesn't make any sense. Fused ring it could be. Doublet ring, that doesn't make any sense. Okay, you see it there. Yeah. So one system is there. Yeah. So what does this suggest? 1.9 singlet, 1 hydrogen, deuterium exchangeable. So what kind of functional group or what kind of thing can be present here? Any guess?
Sir, hydroxyl group.
Hydroxyl group, exactly. Because you know whatever I have discussed in the last lecture also, that OH, NH2, this kind of groups are actually deuterium exchangeable group. Okay, you are seeing one hydrogen. Okay, you are getting a signal nearly 1.9, and also in your formula C5H10O. So there is a chance that OH group is present here. So one group you find out. OH group. Okay. Now singlet 6 hydrogen. What kind of group could be possible? What kind of thing is possible? 6 hydrogen singlet. So 1.3, you understand, 1.3 it actually stands for methyl group, right? So methyl group generally shows 3 hydrogen, and dependent upon there is another carbon which contains how many hydrogens, it will show that kind of pattern, but the position is 1.3 nearby. So you see 6 hydrogen and also a singlet. So another, and position is same, that means 2 methyl groups are there. Okay, and also since you are seeing a singlet, that means the in the nearby this carbon, this will not have any hydrogen, no hydrogen here. Okay, so these two groups that are different, these are not hydrogens. If that is hydrogen, then you will see 6 hydrogen. One, if one is hydrogen, then you will see 6 hydrogen doublet at in the same position. So it is actually not observed here. So generally what's seen, that now you have to go to other data. You see D equals to 6.0, 1 hydrogen, doublet of doublet. Okay, and you are given 2 coupling constant, 17.4 and 10.7. Another is 5.2, 1 hydrogen, doublet of doublet, is 17.4 and 0.9 hertz. And another is 5.0, this is of doublet, another which is 10.9 and 0.9 hertz. So these are the data. You can see from here that these hydrogen, these 2 coupling constants, this is one matching with this, another is with this. Okay, see they are interconnected. So you see here, that this one hydrogen double doublet, here is also one hydrogen double doublet, and here is also another one hydrogen double doublet, doublet of doublet. Okay, and the coupling constants are with each other. Okay, they are similar to each other. Okay, so what is possible that the some hydrogen, it is coupling to another hydrogen and another hydrogen. Okay, so if this couples with this and this couples with this, you will see doublet of doublet. If this couples with this couples with this, you will see doublet of doublet. If this couples with this and this, you will see also doublet. For this you will see doublet, you will see for this it is another doublet. So possibility is that the structure is like this. Okay, and you see a double bond equivalent kind of system. Okay, so this carbon is actually here. And what is the remaining position? It's nothing but OH. Now you just predicted, you have just predicted this could be possible structure. Now you know this carbon and this carbon, two carbon counts the number of carbon, 1, 2, 3, 4, 5, 5 carbons. What is the number of hydrogens? 3, 3, 6, 1, 7, 8, 9, 10, and 1 oxygen you can see. So it is satisfying the molecular formula, right? Okay, so first, now you need to identify which one gives which signal. So first, suppose this, I am naming it HA, HB, and H. This all of these gives 3 double up doublet. So which one is HA? Is 6.01 or 5.2 or 5.0?
6.0.
Why?
Sir, there is a high coupling constant 17.4, which belongs to trans olefinic system.
Exactly.
So
This
and
one?
SC also belongs to 6 ppm.
Exactly.
Sir, trans proton on sp2 hybridized carbon
Mhm.
6.0 value.
Yes, 6.0 exactly. But if you are much more confirmed, if you see this coupling constant, okay, this is a trans coupling constant.
Okay.
Okay, so
Okay,
here this is a trans coupling constant, and you see it is coupling with which one? It is coupling with this one. Okay, 5.2. Here also there is 17.4 coupling. Another coupling is that 10.7. Okay, this is for the cis coupling. And you know the geminal coupling, that is a coupling between two hydrogens in the same carbon. This has very low magnitude. Okay, so which one is this? So these two, this 5.2 and 5.0, you see there is another coupling 0.09 Hz. This belongs to geminal coupling. Here there is no geminal coupling. So that means I am confirmed that this is coming from this one. So HA is the 6.0. Now you see with which it is making the trans coupling. It is making the trans coupling with HC, right? HA is making trans coupling with the HC, and HC which one? Where do we show this trans coupling value of 17.4? So 5.2 is the HC. Okay, and HB, you see what is HB? HC? Which one means 5.0? Yeah. This one you see 5.0. Okay, so this proton will resonate at 5.0 because it is having a cis coupling with this with 10.7 Hz coupling constant and another geminal coupling with this of 0.9 Hz. So whatever structure I have predicted is actually matching with the NMR data that is given there, and also the double bond equivalence is matching. So predicted structure is this one. The ABC just naming are different, but the predicted structure is this. Okay. Okay. So Here's the next question. 1H NMR spectrum of a naturally occurring amino acid is recorded in a DTO-DCl mixture. So you need to find that the structure of any amino acid and explain the splitting pattern. Okay. So you see here, and what kind of pattern is this? A prime BB prime pattern, 4 hydrogen, J equals to 8.0 hertz, and 4.40 triplet 1 hydrogen, J equal to 7 hertz, and 3.30. This is a doublet of AB quartet, which is J equal to 2 values, 15 hertz and 6.8 hertz. Okay. So can you please predict what kind of amino acid or what kind of structure it is possible? Here you have given no clue. Okay. You are not given any kind of chemical composition. You need to predict from the knowledge of your data that what kind of structure is it possible. So I'm going one by one. Okay. Just see from this pattern what you are seeing, A prime BB prime pattern. It is highly possible that what I have said earlier, it is a para-disubstituted compound. Okay, and if you see the chemical seed values nearly 7 or 6, this actually corresponds to this nearly aromatic region. Aromatic region protons generally come between 7, 8, 6 or like that. Okay, so you are supposing that there is a this is a para-disubstituted compound. Okay, now it is you are up to now, and these two groups are different. Okay, so this group, okay. So this group and this group is different. Okay. Now I as much know that amino acid actually contains some NH2 and COOH group. Okay, you know this amino acid is actually contains an amine group and an acid group. So general structure of amino acid is like that. This NH2, this COOH. I am not drawing the zwitteraminic structure. If you anyone tell me that if could be the zwitteraminic structure, I am not drawing that. It is just equivalent form. Okay. So this is H, and this is kind of R kind of thing. Okay. This is the structure of general amino acid. Now you see this. Now I am coming to the second point, that 4.40 triplet, 1 hydrogen triplet. So you know that 1 hydrogen triplet and another information. Yeah, this one, 2 hydrogen doublet of AB quartet, and you have 2 coupling constant values of 15 and the variable one is 6.8. Okay, so this is possible that if since it is saying, okay, one by one I'm going, since it is saying triplet, so there is nearby 2 hydrogens. Okay, and since 3.30 the peak, which is the proton peak, which is showing doublet of an AB quartet. Okay, so there is 1 hydrogen nearby. You can see this hydrogen, you can predict that there is another hydrogen, this will couple, and this is diastereotopic phase. Okay, this hydrogen, if there is another group, this, if there is, suppose what I am saying, if it is kind of thing, and like this one, okay, and you have 2 hydrogens are there. So you know these hydrogens are diastereotopic hydrogen, and they very easily can show what you say is actually they can easily show AB quartet kind of structure. And now you need to just match the splitting pattern. Okay, now I am seeing this hydrogen. Okay, this is 1 hydrogen, there is 2 hydrogens are there, so it will show doublet. And since these 2 hydrogens are diastereotopic hydrogen, so it will show this doublet, and this doublet will be a AB quartet because these 2 AB are different. Okay, and since these are different, hence this will have 2 J values. Okay, and these two hydrogens will show, we'll have a hydrogen here, so it will show and the doublet. Okay. So now if so no more information is given for this any hydrogen, so I can predict that it is actually connected to this one. Okay, so these two hydrogens are there. Here there is another hydrogen, so this should be NH2. Okay, and now since it is a para-disociated compound, so since no information is given here, so I can actually need to put some groups here which actually resembles any kind of amino acid. So what is the amino acid structure you are getting? You are getting some amino acid structure like this. Okay, so you are getting say CH2, CH, one is NH2 here. Yeah. So one thing you will like getting this, and this is second. Okay. So you see that in the first state you were saying A prime, B prime, and 4 hydrogen here, and here you are saying that you are using D2O and DCl medium, so there is a very high chance that OH could be present. But the information regarding OH is not given in the question. So if OH is there, so it actually resembles one kind of amino acid, since you are saying that amino acid, some amino acid is present here. So one kind of amino acid is forming heat, and whose spectra actually matches with the data given here. So this is the amino acid, and what is the name of this amino acid? What is the name?
Tyrosine, sir.
Exactly, tyrosine. So tyrosine is showing this kind of spectrum. This is the structure. Okay. Okay. Now life is making easy. C10H15N molecular formula is given. Okay. Now what I have said you that if you are given first molecular formula first, find what is dPe. C minus H by 2 plus N by 2 plus 1. So this is giving 10 minus 3.
For
Yes. Yes, carry on. Okay. So yeah, so 10 minus 15 by 2 plus half, so this will 7 minus 10 minus 7 3 plus 1 4. So there are 4 there are 4 double bond or double bond equivalent kind of system. Now you are when we were saying this whole data, this data is given here, you first focus, is there any information I can gather from there? Yes, one information I can gather from here, that it is a broad singlet of 2 hydrogen and which is D2 exchangeable. So what kind of functional groups it be present? Functional group of OH and NH2, these two kind of functional groups it could be present. But my molecular formula doesn't say that only kind of oxygen kind of thing could be present here. So only possibility that this NH2 group is present. So my molecule actually contains NH2 group, right? And you see this is showing 2 hydrogen broad singlet. Okay, singlet. That means there is no nearby hydrogen coupled with. Okay, so this information what I have said you, that first see any kind of D2O, this whenever you are seeing any nitrogen or oxygen compound, you just focus that if there is any kind of information regarding this NH2 or OH kind of group present, because you can see that is a broad singlet or broad signal, or this is deuterium oxide exchangeable. Okay, now the first thing, you are showing 6.9 and 6.6 delta, this A prime BB prime pattern, 4 hydrogen, and J equals to 8.0. Okay, so there is a high chance that this is a, what is this? The same thing in the last question. This is 4 hydrogen, J equal to 8.0, A by P prime BB prime pattern. You can just close your eyes and just write it. This is a para disubstituted compound. Okay. And this range I have told you about is 6.678. In this range, generally benzene protons come, and we can if you don't believe it, then you will see that other proton peaks and these peaks that will be different here. So this hydrogen, this is hydrogen, all hydrogens are different. Okay, now you see other, now you are going to the other spectrum. 2.5 triplet, 1.5 quintet, 1.3 sextet, 0.9 3 hydrogen triplet. So what is the possibility that this 3 hydrogen singlet? 3 hydrogen singlet is actually coming from the methyl group. Okay, methyl group is showing 0.9 3 hydrogen singlet. But someone of you may question that in the earlier case you have said that methyl comes in like where it was for methyl group was 1.3 singlet. Yeah, 1.3 singlet. But here you are seeing 0.9. So in that case, that was more distillate because it is giving a higher delta value. Here it is in lower delta value. Why? Why that was showing in 1.3?
There was a olefinic system,
Mhm.
so somehow it distilled that methyl group.
Okay, I am going to the structure.
There is a cone-like structure coming out in which the outer periphery, at the periphery, the hydrogens are decoupled, and the center they are shielded.
Okay, actually this whole group, whatever you are seeing, it is far away. Okay, so that much anisotropy.
Sir, there is also a electronegative atom oxygen hydroxyl group.
Exactly. This is the main reason. This is the main reason. This oxygen which it is actually reducing the electron density. So it will be more distilled, it will have higher delta value, whatever you have learned, and you are seeing here right there, 1.3. Here, that means it is not connected to any kind of electronegative element, so it is showing 0.9. Okay. So you can see these 3 hydrogen and it is showing triplet. So triplet presence means which is it's connected is hydrocarbon. This will contain how many hydrogen? 2 hydrogens. Okay. So it will show triplet. 2 hydrogen, these hydrogen, 3 hydrogen, 2 hydrogen, 2 plus 1, 3. So 3 hydrogen triplet. So it will know so 0.3. Now these 2 hydrogens, how should it show? Here 2 hydrogen patterns are almost too much. 3 2 hydrogen patterns. Okay. So you see it can couple to any kind of group. Okay, so if 2, so it is 3. Okay, so 2 hydrogen, there is 3. If there is another CH2, okay, so it will be 5, then 6. Okay, 6 state, right? So this CH2 is actually connected to the 2. Here may be another CH2. If this is possible, then this 2 hydrogen, this 2 and this 2, 4 plus 1 5. So I expect I will expect that this will be 2 hydrogen quintet. 5 for 9 pattern. Okay, I am seeing a 2 hydrogen quintet like there. And this CH2, then what about this CH2? Is it coupling with another CH2? Is it possible? See, 2 plus 2 4 plus 1 5. So I don't see any another quintet. Okay. Now since you are seeing that these are coming closer to the benzene ring, So you see there are more desilted. Here this is 0.9. Here this is 1.3. Here this is 1.5. So this is a chance that there is no CH2 again. So there is a chance that it is directly connected to this benzene ring. In that case, is the pattern matches? Yes. You see, this is 2 hydrogen and there is 2, so 3. So 2 hydrogen triplet. And since it is very closer to benzene, it will have higher delta value. You will see 2 hydrogen triplet 2.5. Okay. So, and you see all the coupling constants are equal. This actually suggested that there is a long hydrocarbon chain. Okay. You are again confirming it from here that there is a long hydrocarbon chain that all hydrogens are equal. So now what about this NH2 group? Since one position is left, so if any position carbon is left here, this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9. I missed one. Check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, 10. This one I missed. 10. So see 10. Hydrogen 3 to 5 to 7 to 9, 10, 11, 12, 13. And if NH2 is present, 15. H13, okay, I'm writing H13 and no other group. So what I am left with, if in the formula you see this, I'm left with this NH2. And since I know this is a para-disubstituted compound, so that should be the structure. So see here, okay, just reversal. Fine. So this will be the structure. Okay, coming to the next problem, that you have to identify the structure of the organic compound from the given data. This is compound is derived from 2-methylphenol. What should be the structure of 2-methylphenol? This is 2-methylphenol. This is phenol. In the second position, there is a methyl. Okay. Now, the structural formula you are given C9H10O2. This is the structural formula that you are given here. Okay. Now, you have to find what I have said, dBe. What is the dB? dB is 9 minus 10 by 2.
5.
5. Yeah, 5, right. Plus n by 2 is no nitrogen plus 1. So 5, 4, 4 plus 1, 5. So there will be 5 double bond or equivalent kind of system. So these 3 double bond you are seeing in the benzene. So another 2 double bond or double bond kind of system that could be present. Now I am just need to analyze the formula. So here you see this the D equal to 8.2, 1 hydrogen D2 exchangeable. You can just close your eyes and which is possible. This one. Okay, this is deuterium exchangeable OH. Now 8.2 deuterium exchangeable OH. This must be this one. Okay, since there is a benzene ring, this is the oxygen. So this proton, this OH hydrogen, this will be very much desilted. Okay. Now this methyl group, okay, I'm just rubbing it up and like CH3. Now I need to consider what other kinds of groups will be present. Now you see the list here. So one oxygen I have taken for this oxygen for phenol. So another oxygen I am left with. Okay. So what is the possibility? If you go back, you can see, yeah, Z equals to 7.4, J equals to 7.4. Doublet, 1 hydrogen. This is doublet, 1 hydrogen. Okay. So this is possible that this is coming due to which kind of thing? So I am expecting that these are protons are there, right? Okay, so the proton which is very closer to OH, this is a more distillate. Okay, so going back, okay, first coming back from the backward. So methyl, 3 hydrogen, it is coming to singlet. 3 hydrogen singlet is there. Yes, 2 possibility there. 2 possibility are there. 3 hydrogen singlet. 2.3 and 2.6. Okay. So which one should be due to this methyl? Which is the one due to this one? 2.3 or 2.6. Since it is connected to the benzene ring, it is actually coming 2.6. So this hydrogen actually is much more distillate. And also this is coming from methyl hydrogen, 3 hydrogen singlet, and there is no other group there, and it is coming 2.3. So if you see any kind of spectrum, where you see 3 hydrogen singlet or 3 hydrogen singlet kind of thing at 2.1, 2.2, 2.3 ppm, you just need you can tell presence of this group. Which is this group? What is this called?
Keto group.
This total. This total one I am taking. This is ketone and this is methyl. So this is called ketomethyl group. So normal methyl generally gives you, we have seen in the last question, normal methyl actually gives a peak like 0.91 like that. Okay. So it is coming to any OH, then it is more distillate, but generally 2.1, 2.2 kind of ppm, there generally presence of ketomethyl system is generally understandable. Okay. So here I am predicting, not pretty sure, that ketomethyl groups could be present. Okay. So if ketomethyl group is present, then what you will see that number of hydrogens. So since it is this compound is derived from 2-methyl phenol, so there is a chance that this group or something along with this group is positioned in the benzene ring. Okay. So if this is positioned here, I'm taking another. Suppose this group, or suppose any group, suppose D kind of group. No, don't confuse it with deuterium. Okay, so in another name. Suppose chemistry is difficult to get names. X, okay, suppose it is some X. Okay. So how many different protons will be there? 1, 2, 3. Okay. So if this is placed here or here, you will see 3 different kinds of protons. So this will show how much signal. This will show if there is, suppose there is X. If there is X, so it will show doublet, it will show triplet, it will show doublet. So I expect 2 doublet and 1 singlet. Okay. So 2 doublet and 1 triplet, because here hydrogen, this hydrogen will show triplet. Okay. So here I see that this is doublet, and here it is a singlet. So this is not possible here. Is this possible here? Same thing you will see. So either it is possible here or it is possible here. Now I am writing the structure again. Suppose this X group is here. Okay. So how many different hydrogens will be there? This is H1. This is H2. H3. Okay. If this is placed in place of H2, here X is there, then how many will be there? It's hydrogen, H2, H3. Okay, so this hydrogen will show doublet, right? There is no equivalent hydrogen nearby. This hydrogen H2 will show, this is one hydrogen, so it will show doublet. Sorry, this will show singlet. There is no equivalent hydrogen nearby. And this hydrogen, it will also show doublet because there is another hydrogen. Is this the same case here? Yes, H3, it will show singlet. This will show doublet. And this, again, this will show, oh my god, mistakes. This is doublet. Because why this is doublet? Because this is coupling with this one. This is doublet because this is coupling with this one. But this is coupling with none, so it will be singlet. So two kind of structures are possible. Now, is this two equivalent? No, these two are not equivalent. Okay, because here this X group, this will be para, this meta to OH, and here this is para to OH. So they are not equivalent. And here also you can see that one singlet hydrogen, this is not coupled to anybody. And here this doublet hydrogen, they have similar coupling constant. That means this kind of structure is predicted. Okay. Now you see this doublet, in this doublet, one thing is very interesting. These two hydrogens, here you see 7.8 singlet. Yeah. You see here 7.8 singlet. 7.8 singlet, and there these two coupling partners, one is 7.7 doublet and one is 6.9 doublet. Okay. So if this is the structure, if this is the structure, you will never see any hydrogen close to methyl. Okay. And here there is another hydrogen. This pattern you will not see there. With this doublet coupling, this doublet and this much of delta value you will not observe. You will observe such delta value if there is very close to OH. This doublet value is very close to OH. See here, doublet value. Yeah. So these two hydrogens are between CH3 and this X group. OH is not interfering here. So you don't need to have much more delta value for these two hydrogens. But whatever you're seeing, that singlet value is matching with this doublet value. Yeah, the singlet value is matching with this doublet value. So that means these two hydrogens are actually very close or nearby to this OH. Okay. So this is the possible structure. Possible structure. If I consider this coupling of this proton. Okay. Now, if this is the possible structure, can you just total count it? Yes, carbon 1, 2, 3, 4, 5. Okay, 6 carbon in the benzene. Okay, here one carbon, 7. So I have 9. So I have predicted that one ketomethyl group would be present. Okay, one ketomethyl group could be present. So another, so total 8, 9. Total carbon is matching. If only ketomethyl is present, and I am assuming that no other groups are there. Hydrogen 1, 2, 3, 3, 3, 6, 1, 7, 7, and here 3, 10. Yes, matching. And 2 oxygens are there in ketomethyl 1 and phenol 1. So this is the compound we're looking for. This is the compound. This is directly attached to here. This is CH3 and this is H. Okay. So next question is identify the structure of the organic compound from the given data. This molecule, it is already questioned that amide functional group. What is amide group? What is amide group?
CONH2.
CONH2. Yes. This is the amide group. So the question you are given that amide group is there in your sample. You have some amide group, and also it is given that your compound structure is C10H13 NO2. So first of all, first come first, dBE, I need to find it out. dBE is 10 minus 13 by 2 plus n by 2 plus 1. So this will be 10 minus 6, that will be 4, 4 and 1, this is 5. Okay. So there is 5 double bond or double bond equivalent systems. So,
Sir,
yes,
sir, last question we have saw the DBE is equal to 5, sir. Then there is only 4 double bonds are present.
here, yes, yes,
Yes, sir. The one double bond is missing.
double bond.
Sir, sir, DBE value is 5, sir. There is only 4 double bonds are present here.
Oh, yeah. So what I have said that DB is actually stands for double bond or double bond equivalent system. Actually, in such cases, OH can also act, or O bond. It can, you know, that it can undergo this resonance. Okay, so this single bond, what is you are seeing here, that's not actually single. It is single or double. Okay, so 5 double bond or double bond equivalent system that I was talking about. Okay, so OH bond is actually can act as a double bonding system. You understand that? CO bond.
Sir.
Sorry, I cannot get you.
Okay, sir, I can understand.
You understand? Okay. OH on NH kind of bond that actually undergo resonance. So this single bond actually have double bond kind of characters. So this is equivalent to a double bond. Okay. Yeah. Now, coming here. And so dB is 5. Now, sorry, I have shown the structure. Okay. So now I am just looking to the data. So first delta is 9.6. You see, broad, singlet, 1 hydrogen, D2O exchangeable. What is this presence? D2O exchangeable. So there is a presence of either OH group or H group. Okay. 1 hydrogen, singlet, broad, D2O exchangeable. So if you are, since you are seeing that only this NH2 group, it is already mentioned in the questions, and only one signal is there for D2O exchangeable nature, so there is a chance that this is coming due to this group, right? Why OH? I am just not ignoring OH because in my system there is said, they have said that you have CONH2 group already. Okay. In the signal, you are seeing one broad singlet, 1 hydrogen, D2 exchangeable. So NH2, it is not anything else. Okay. Now, is this really NH2 or something else? That we need to find out. So if NH2, what you will see, this is 2 hydrogen. Okay. And if there is no girl, nothing is there. So you expect this is singlet. Okay. But you are seeing 1 hydrogen singlet, right? You are seeing this 1 hydrogen singlet. So what happens? That 1 hydrogen is missing here. So 1 hydrogen is actually accommodated to another bond, right? Since you are seeing 1 hydrogen singlet for NH group, so this is not NH2, it's NH. And to make it 1 hydrogen single, there is no hydrogen here. this group will be something, this carbon will have no hydrogen. Up to now, I have understood. Now, going back. Yeah. You can see from there, 2.05 singlet 3 hydrogen. What is possible? I just mentioned in the last question that this is the presence of ketomethyl group. Is there any possibility? Yes. If ketomethyl is there is generally gives pig at 2.05. Okay. So this part is solved. This is attaching CH3, CO, NH, and this is attached to someone else. Now, you are seeing 1.4 triplet 3 hydrogen J7.0, and similar J7.0 is observed 2 hydrogen quintet. Again, I am repeating, you are seeing 1.4 triplet 3 hydrogen J7 arch, and 4.0 you are observing quartet 2 hydrogen J7. Okay, so same coupling constant, that means these two carbon, the protons and the two carbons, they are very coupled. And also this nature, this type of splitting actually indicates that this triplet 3 hydrogen is actually, and also the quintet for this 2 hydrogen, this is a very chance that CH2 CH3 group or ethyl group could be present. How I know? Because this will show 3 hydrogen, this will 2 plus 1, so 3 will be 3 hydrogen triplet. Yeah, and this will be 2 hydrogen 3 and 4. So this will be 2 hydrogen quartet. But now I can assume that there is another carbon, some groups will be there, so there should be another thing. Okay. But if CH2 is attaching to any carbon, it will never show such high value of this chemical shift. This high value indicates that this is attaching to any electronegative element. And you are seeing your compound is rich with oxygen, because nitrogen is used up, there is possibility that this is attached with oxygen, right? So if this OET group or ethoxy group is present, it will show 2 hydrogen quartet at 4, and this will show 3 hydrogen triplet, but since it is allied to oxygen, so it will have higher delta value, right? So this one is done, this one is done, this one is done, this one is done. Now you see J equal to 8.0, J equal to 8.0, doublet 2 hydrogen, doublet 2 hydrogen. Okay, what this actually suggests? This actually suggests the para-disubstituted compound. Okay, ignoring the second order effects, this is a para-disubstituted compound. So this one couples with this. Okay, so this is a doublet. Similarly, this couples with this is a doublet, and ignoring the second order coupling, these 2 hydrogen, I can say that they are chemically equivalent. Similarly, if I compare this now, C1, 2, 3, 4, 5, 6 carbon, this one, this, where is this? This one, yeah, 7, 8, 9, 10. You can see, good. 10 hydrogen, 1, 2, 3, 4, and some groups will be there. 1, 2, 3, 4, 3 here, 7, 2, 9, here 3, 12, and here is 1, NH, 13 is matching. That means this NH is actually attached to this benzene ring directly, and this O is attaching to this one. Then you see all the patterns are matching. Okay, so this is the structure, that ethoxy NHCOCH3. Okay. Now coming to the last question for today, you have to sketch the 1H NMR spectrum. You can sketch it of 135 trioxane at room temperature and at -80 degrees Celsius. The slow exchange of the equilibrium shown below. So what should be the pattern, or what should be your answer? Anybody guess? Okay, what will happen at room temperature? At room temperature and at minus 80 degrees Celsius. So what should be the difference? If you understand that, you will be able.
Sir, at room temperature, there will be one signal due to axial equatorial flipping of the ring. And at minus 80, there should be two signals, maybe.
Which one will be higher?
Higher. Sir, axial has higher chemical shift value.
No. Your answer is correct. So at room temperature, all will be single peak. Okay. But at 80 Kelvin, two different peaks will be there. So this is the answer. That at room temperature, what happens? Rapid interconversion. Okay. So if these two forms are in equilibrium, okay, so the barrier between them is actually achieved at room temperature. So which form is present, you cannot detect because they are easily changing. Okay. Suppose this is a one form, this is rapidly changing its form. Okay. So you cannot distinguish between them. But what happens at minus 80 degrees Celsius? Minus 80 degrees Celsius, it happens that the flipping or the interconversion between them, the barrier is low. Why it is low? You must be questioned that barrier is same. Why barrier is low? What you were talking is low. So suppose in this actually looks like this one. So from this state, suppose it's going to this state. So this barrier is same, right? So a barrier, how you say that barrier is changing? Barrier is not changing, but the energy you need to cross the barrier is not provided at the low temperature. So what I'm saying, this energy difference, you know what is about activation energy, so you need to give this activation energy at very low temperature. This is not possible.
You are saying,
Yeah.
right? You are saying kinetic effect, right? That is the thermodynamic effect, this is the kinetic
Exactly.
effect. Right?
So if you cannot provide this thermal energy, it will not go to that state. So it will show this state. Okay. So at room temperature, rapid interconversion is possible. So what will happen at room temperature? You cannot distinguish which one is equatorial, which one is axial, because they are flipping at a very fast rate. You will see only one peak, and that will be at 3.5 and high peak because it is attached to any oxygen atom. Okay. Now,
In room temperature, rate of reaction is higher actually compared to lower temperature, right? You are saying?
yes, here not the rate of reaction, here the rate of interconversion.
Yes. That means there is an intermediate, right? So that's why.
Yes, there is some intermediate. Then this actually crosses the barrier and this goes to the another state. Yeah. Okay. So at room temperature, only single peak is there. It will be at 3.5 ppm. So only one peak is there. But what happened at minus 80 degrees Celsius? That you will see ring has a flipping has a barrier, and axial and equatorial hydrogen will have different delta value. They will show what kind of structure? AB quartet kind of structure. Okay, and delta values are very close, so there is very high chance that they will show AB quartet kind of structure. Delta values are 3.4 and 3.6 ppm for axial and equatorial hydrogen. Okay, so you will see two different peaks at the 80 Kelvin and but minus 80 Kelvin, minus 80 degrees Celsius, but at room temperature we will show only one peak. Now the question I was asking that if this is the structure, this is the axial hydrogen and this is the equatorial hydrogen. So if suppose there is oxygen here, so between HA and HE, which one has higher delta value? Someone told me that HA. Anybody else?
Equatorial.
Equatorial. Why?
Anisotropic effect.
Anisotropy of what?
Sigma bond anisotropy.
Exactly, a beta compound, this bond anisotropy, beta bond anisotropy. There is a special case that for this beta bond anisotropy, there is a chance that this equilibrium, this equatorial hydrogen will show higher delta value, like 3.6 ppm, and hence it will show a very less change, it will be 3.4 ppm. And since these two are very close, there is a chance that they will show maybe quadrant kind of structure. Okay. So these are the questions of this week that I have discussed. This will be help to do your assignment. So if anybody have any questions, you can really ask me. Yes. So anybody have any questions? Prakash Mandal, these are certain assignment questions. We don't. Yeah, you are correct, but I think they have no questions. They have not created actually. So if this kind of assignment one, then is beneficial for you, right? Have solved that, it will be helpful for you.
Yes, sir. No problem.
Okay. Yeah. Anybody else? Okay, so if there is no question, so I am stopping the session. Yeah.
Thank you.
Well.